Let us know the chapter probability. Probability combination. If n objects are given and we have to select r out of them, r less than equal to n, and order of selection is not important. Such a selection is called combination of n objects taken r at a time. The number of ways of selecting r objects out of n given objects nc1 ncr equal to n factorial upon r factorial n minus r factorial, where r less than equal to n. We have nc0 nc1 equal to n equal to 1, nc r equal to n minus r, nc n minus r. Permutation. Permutation. If n objects are given and we have to arrange r less than equal to n out of them on a line, and order in which these objects are arranged is important. Okay, arranged is important. Is called permutation of n objects taken r at a r less than equal to n. We have npn equal to n factorial. np1 equals to n, and n factorial is n minus 1, n minus 2 up to 1. 0 factorial is 1. Look this. Random experiment. Tossing of unbiased coin. Sample space is head and tail. Tossing twice. Sample space is head head, head tail, tail head, tail tail. Tossing the three unbiased coin. H H H H H T H T T triple T T H H T H T T T H T H T. Next is throwing a fair die. Sample space is 1, 2, 3, 4, 5, 6. Tossing fair die. Throwing of two fair dice. S is equal to 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1 up to 6, 6. So in a general, n of s is equal to a to the power b, where a is equal to number of outcomes of each object, and b is equal to number of objects. N is number of outcomes of the each object, and b is number of objects. Next is pack of cards. Total cards without joker 52. In that 26 red cards, 26 black cards. In that 13 hearts, 13 diamonds, 13 clubs, 13 spade. One suit is equal to 13 cards. Face cards, 4 kings plus 4 queens plus 4 jacks. Look this. Complement of a event a dash or a bar equal to x, where x belongs to s, x not belongs to a. Next is a union a dash equal to s, a intersection b dash equal to phi, a dash of dash equal to a. Next is definition of probability of probability. Let S be the sample space associated with a random experiment, and let A be a subject of S representing an event. Then probability of an event A is P of A equal to n of A upon n of S. This is the definition of probability. From above discussion, definition 0 less than equal to PA less than equal to 1. P of S equal to 1. P of phi equal to 0. P of A dash equal to 1 minus P of A. addition theorem. If A and B are two event of sample space yes, then prove that P of A union B equal to P of A plus P of B minus P of A intersection B. If A and B are mutually exclusive event, P of A intersection B equal to 0, P of A union B equal to P of A plus P of B. If A comma B comma C are three events of a sample space S, then P of A union B union C equal to P of A, P of B plus P of C minus P of A intersection B, B intersection C, P of A intersection C plus P of A intersection B intersection C. Fourth, if A comma B comma C be the two events of a sample space, yes, then P of A bar intersection B equal to P of B into P of A intersection B. If A, B, C are mutually exclusive events, then P of A union B union C equal to P of A plus P of B, P of C. P of A intersection B dash equal to P of A minus P of A intersection B. Look this. Conditional probability. The probability of a events A the probability of events A when the event B has already occurred is called the conditional probability of A when B is given and is denoted as P intersection V, then conditional probability is meaningful meaningful when P of B equal to not equal to 0. So P of A when B equal to number of A intersection B upon n of A equal to P of A intersection B upon P of B. P of B intersection A, P of A intersection B, P of A, where P of A not equal to 0. Multiplication theorem. Multiplication theorem. If A and B are two events in the sample space S, then P of A intersection B, P of A if P of A not equal to 0, P of B into P of A on B if P of B not equal to 0. If A and B are independent event of sample space S, then P of A intersection B equal to P of A into P of B. Notations. Not A, A bar, A and B A and B, A and B both occur A intersection B. Fourth one, A but not B. A intersection B bar 5. B but not A. A intersection by B. A bar intersection B. 6. Neither A nor B equals to A bar intersection B bar equal to A union B is to bar. At least one of A, B, C, A union B union C. Look this properties. Next is exactly one of A and B. A intersection B dash union A bar intersection B. All three of A, B, C. A intersection B intersection C. Next property is exactly two of A comma B and C. A intersection B intersection C dash union A intersection B dash intersection C union A bar intersection B intersection C. These are the properties of probability. Bayes theorem. Let S be the sample space and let E1, E2 be a n mutually exclusive and exhaustive event associated with a random experiment. If A is any event which occurs with E1 or E2. Then P of EI upon A equal to P of EI into P of A upon EI divided by summation of P of E1, P of A E1, I equal to 1 to n, I equal to 1, 2, 3, up to n. This is called Bayes' theorem. This is a theory required to solve the problems on probability. Number 1 problem. Two dice are thrown. The number of sample points in the space when 6 does not expect on any one side is. So here n of is equal to 6 multiplied by 6, 36. N of equal to 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Similarly, 2, 2, 1, 2, 2, 2, 3, up to 2, 5. Like that, 5, 5. So P of A equal to n of A upon n of S, 25 upon 36. In a sample space, it is said that 6 should not come when die is thrown. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5 are expected, but 1, 6 is not expected. So if we calculate such a number of elements, we get 36 out of 25. Next is two unbiased dice are thrown. The probability that the product of number on their upper face is 12. So let n of s is equal to 36. The sum of the scores on their upper face is multiple of 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 6, 6. So we get n of a equal to 6, hence p of a equal to n of a upon n of s, 6 upon 36, 1 by 6. That's all.